As we continue to discuss the properties of the photoreceptors, it's important first now to go through this process of transduction. So transduction, that magical thing that happens that allows us to take that stimulus energy from the environment and turn it into something the brain can understand. To discuss transduction and what's going on in the photoreceptors, we're going to start by looking at a photoreceptor. So the image on the left there, in the left part of that picture, is giving us the basic structure of a rod, of the rod's photoreceptors. There's an inner segment, an outer segment. What we're actually going to magnify, what's being magnified there is part of the outer segment. And remember, that's what's fleshed up against the pigment epithelium. And then on the other side, we have, so we get to the inner segment where we have our soma cell body and our synaptic terminal or synaptic peduncle, or basically where the synapse is and where we're going to communicate to those horizontal cells and to the bipolar cells. So we're looking at that outer segment. This outer segment contains these stacked discs. Okay, and what that magnification is showing you is a couple of those outer segments where they are separated by a membrane, and then there's this little tack looking thing, and then they've gone and magnified that as well. And when we magnify one of those, what we see is a visual pigment molecule, okay, which is made up of the opsin. So and they're magnifying that to show this opsin that's snaking across those membranes. If you count the number of times that snakes across that membrane, or those membranes, it's 7 times across the membranes that are separating the outer discs. That's the opsin. And then on that opsin, you can see there is one tiny, it's colored in blue. There's this one tiny molecule of retinal. And it's the opsin and the retinal together that make up what's called rhodopsin, where the RHOD actually comes from the fact that we are going to see that we have a reddish hue to our visual pigment. Here we're looking at that rhodopsin again, where in the top right we're seeing it snake across the membranes there in the outer discs. But now we're going to take that, we're going to magnify it again so that we can see that retinal. Remember, the retinal is a really tiny molecule. That's actually what's going to be doing the absorbing a photon of light when it hits that photoreceptor. So if we magnify that retinal, and we see this at the bottom, when we're looking at the retinal and we can actually see what's going on with it, we're seeing just a little teeny tiny piece, right, of the opsin strand, that long strand of opsin. And when we're in the dark, this is when we have this reddish hue to the retina because of the rhodopsin and the coloring that it has. And so when we're in the dark, that retinal is bent over and it's attached to the opsin. And then if we go into the light and that rod fires because that retinal is absorbing the photon of light. And when it does that, it isomerizes. So that says retinal isomerized by light. It isomerizes, which means it changes shape, it straightens out, and it actually breaks off from the opsin. Look at this process of transduction. Transduction. The light is absorbed by the retinal. The retinal undergoes isomerization, which basically just means changing shape in this chemical sense. And the bond between the opsin and the retinal is broken, and that causes an enzyme cascade that we're going to say affects the entire receptor. And we usually talk about this as affecting other retinals so that the same process happens, and so the whole rod fires. It's a tiny bit different than that, but we're going to leave that. When the retinal, when that isomerizes and changes shape, it causes an enzyme cascade. So enzymes acting as these messengers, so the whole rod fires. Or actually, we're going to say hyperpolarizes, it stops firing. What happens then? So if we walk back through this with my little arrows, I often do these, like, here's a really shortened version of everything we just said. So photon of light, retinal absorbs that energy, changes shape, isomerizes, breaks from the opsin, triggers this electrical event. We have transduction, and then we see that we go from that bent over. So if we're looking at the picture that bent over, when our retina, this is actually a frog retina picture at the bottom, it has that reddish hue. And then when we see the isomerization and the change, we have bleached out. So the frog goes into the light, and many of those rods fire because the retinals are absorbing the light. And so now we have this bleached out appearance to the retina. And so actually at this point, that rod isn't usable again. It has to regenerate. We have to go through this visual pigment regeneration. And there are enzymes, they're actually in the pigment epithelium that allow for the retinal and the opsin to reunite. And we've looked at rods, but the same kind of thing is happening with cones. For rods, the timing that it takes, the amount of time it takes for this visual pigment regeneration is about 30 minutes. For cones, the time that it takes for the retinal and opsin to reattach and the retinal to go back to its original shape, it takes about 6 minutes. So we have this short aside into transduction, which isn't really an aside, but is the whole reason, right, that we have any experience at all of anything in the world, is that we have to transduce that information into action potentials, into what the brain understands. But now we get to the functional significance. We went through some clinical issues, and now we're going to get to, you're going to see why we see those particular outcomes when we see different, whether it's the macular degeneration and we're losing our cones, or whether it's the retinitis pigmentosa and we're losing our rods, at least first. And so I asked this question about dark adaptation. We come back to this picture that I showed before for just using our classical psychophysical methods. We actually learned about dark adaptation using the method of adjustment, so the quick and dirty. But we did this across, or people, scientists did this across enough participants that it's okay to have the quick and dirty because we're just taking an average across many participants. If we look at dark adaptation, I have this question, and you might want to pause it and just think about this for a moment. So which photoreceptors are helping us to see in dim light? And you want to go back to your notes, go back to your questions, go back to what's helping you to figure out some of this information. If you remember, sensitivity to dim light, we're given that because of the rods, right? That they are having the convergence. They have 120 to 1 kind of convergence, and it's because of that convergence that allows me to see in dim light. But we also just saw, right, that they take 30 minutes to regenerate. So we walk into a dark area, movie theater, whatever, where it's dark, and at first it's going to look like our picture on the left. It takes quite a while for us to get to the picture on the right, where we can actually see that kind of shadow in the background as our rods are regenerating and giving us that ability to see in dim light. And the way we discovered this was through using the method of adjustment. And so the way they did this for the dark adaptation curve altogether, so when we're going to look at this curve, is they had somebody looking at the fixation point, and then you can see there's a test light off to the right there. And so we're going to start with the eye and then everything in the light, and then we're going to turn off the lights, and we're going to look at your adaptation to the dark and how dim can you get that flashing test light with the method of adjustment. So they tested people with this flashing test light in the peripheral vision. Okay, they're looking at the fixation point, and we're going to look at first at that red line, which is just the regular dark adaptation curve it includes really both the rods and the cones because we're looking at peripheral vision, right? I have both rods and cones in the peripheral retina. One thing you'll notice, so something important to start with on this figure is that on the y-axis, it is labeled as logarithm of sensitivity. We're really looking at threshold. So as I'm lowering and lowering, right, with the method of adjustment, I'm lowering and lowering that flashing test light, making it dimmer and dimmer. My threshold's getting lower and lower, which means my sensitivity is getting higher and higher, right? And the other thing you'll notice is the dot where it's pointing to and it says cone light adapted sensitivity. That's where we're going to start. So we're going to start with the lights on. With the lights on, I can only get that flashing test light so low, or else it gets hard to see, right? Because there are other lights. And then we turn off the lights, and boom, already we're down at where the red line starts. I can get that a little bit lower as soon as I turn off the lights, because now that's the only light in the room. And then we look across time, and you'll notice that I get better and better and better across time, where that threshold's going down and down and down until about 6 minutes out. What happens at about 6 minutes out? All of my cones have regenerated, right? They take about 6 minutes to regenerate, and I'm in the dark, so my cones are regenerating. So we have this kind of plateau that you can see. But then, as we get to about 8-9 minutes out, after a little bit of a plateau, we can see that I can start lowering that flashing test light again. And it gets lower and lower and lower until I get to my dark adapted sensitivity, my maximum sensitivity to that flashing test light. So that's the dark adaptation curve. And I'm going to show here how both the cones and the rods are giving us that curve. And again, at first it is the cones. And so we'll start with what happens if I move that test light into where it's at the fixation point. At the fixation point, that's my foveal vision. And so I only have cones and I have no rods. And what we see is lights are on, flashing test light. I'm at the same place I was before because that's the cone light adapted sensitivity. We turn off the lights and boom, I'm down to where the red line is. And then you'll see we get lower and lower and lower, and it plateaus at about 6 minutes, and it stays there. The green curve is the finishing up with the cones. I just plateau and I just stay there. If I only had my cones, this is as good as I'm going to get. And then they brought in people who were rod monochromats. So people who are monochromats, they basically have no cones. This is a very rare disorder where you only have rods. You have very poor daytime vision because your rods are all bleached out, and so bright light, it's really, really difficult for you to see, and you're also going to see only in black and white. But so they bring in these rod monochromats. They do the same exact test with them, and what you can see is the rod light adapted sensitivity, that little dot that's being pointed to, they have a really high threshold. They need that light to be really quite bright, much brighter than a person who has their cones, right, for them to be able to see it. Turn off the lights, and we see this drop off where I can turn that flashing test light lower, and we can see with the purple curve that is showing me just the rods, just the pure rod curve. I'm lowering and lowering and lowering it, and you can see that this would be happening with our rods, but it's for quote normal people, but it's behind the scenes, right? They're not helping us because the cones are what are helping us to see. But these people, they're going to get lower and lower and lower, and then when we get to about 7, 8, maybe 9 minutes out, where that plateau starts to get lower again for us, the rod monochromats catch up, and their sensitivity, their maximum sensitivity is the same. They continue to lower and lower and lower that, just like we did when it was in the periphery, because the rods are helping us to see in that dim light. And it does take a good 25 minutes or so, which is always something to keep in mind when you're having your bright lights on at night. that if you are bleaching out someone's rods, they're going to take time now to readapt to the dark. The other aspect of functional significance that is important to talk about here, we saw when we looked at the clinical issue of macular degeneration. If you remember, there's this kind of blurry spot in the middle, but there's also just black and white vision. What's degenerating there, or what are dying off, are the cones, and they're giving us our color vision. And the way they measured this was by getting spectral sensitivity curves. So looking at the sensitivity of the various photoreceptors that are in the retina. If we look at rod vision, what happens with the rods is they are maximally sensitive to about 500 nanometers. And if we look at the cones, they are maximally sensitive to about 560 nanometers. You can see that each of them has a kind of normal-ish looking distribution where they are sensitive to other nanometers or wavelengths of light, but that this is where they are maximally sensitive. And then there is also a point where we're not sensitive to various wavelengths of light. So it looks like the rod vision, for example, isn't going to see those longer wavelengths of light. We're not going to see those at night when we're basically using our rods. The way they measured these spectral sensitivities was to use a monochromatic light and then determine the threshold at different specific wavelengths. So if you remember when we looked at the property of the stimulus before of electromagnetic energy, we looked at these wavelengths and we said from peak to peak, that wavelength tells me about the color, the height of the waveform tells me about the brightness, but actually we usually aren't seeing a rainbow red that is of this particular wavelength. What we see is a mixture of those wavelengths. Okay, so but now they're in for testing spectral sensitivity. What they'll take, let's just say 500 nanometers, that single wavelength, and they'll present it to somebody and they'll determine the threshold. And then they do it for 510 nanometers and then for 520. So they separate each of those out and show one wavelength or hue. The measuring threshold for light is lowest in the middle of the spectrum if we're looking across, so if we're using all of our photoreceptors, and you can see this in the top figure. And then sensitivity, sensitivity is going to be 1 over threshold. So we're going to see sensitivity is highest in the middle of that spectrum. And remember, this is an important thing to say at least once, but more than once and as many times as I can. When you're reading in the field and they're talking about sensitivity or threshold, you really need to see which one are they talking about and which one are they giving me on the figure. Because if they're talking about sensitivity being high and things are getting where they're showing things getting lower on the figure, then the figure is showing you threshold, right? We measure people's thresholds to get an idea of their sensitivity, and it makes it really complicated, and you just really have to look at your figures and then read the interpretation and make sure you're putting those things together in a way that makes sense. So what's being shown here is the absorption spectra for the rods and 3 types of cones. And so again, if we're looking at the rods, they're maximally sensitive to 500 nanometers. But then the reason the cones are giving us this color vision is because we have these 3 different types of cones. And so short wavelength cones, or what's marked with an S there, they're going to respond maximally to about 419 nanometers. Medium wavelength cones, what's marked with an M, they're going to respond maximally at 531 nanometers. And then long wavelength cones, they're going to respond maximally, so they do the best absorption at 558 nanometers. And so if we think about what's happening when I'm looking at something that is on the yellow part of the spectrum, let's just go to about 558 nanometers, where the long wavelength cones are firing the strongest. The medium wavelength cones are firing, but not as strongly. the short wavelength cones are not firing at all. And if we look at that ratio of how much are those three different types of cones firing, that tells us this is yellow. And if we move to somewhere in the green, let's say 519 nanometers, the medium wavelength cones are going to be firing the strongest, and then come the long wavelength cones, and the short wavelength cones are going to be firing, but almost not at all, right? So now it's that ratio that's telling me now we're in the green. And so it is because we have these three different kinds of cones, and we're looking at these relative firing rates that gives us our rich color vision for our sliver there of our electromagnetic spectrum. And we're going to finish up with the basics of the eye by going back through our review of what's happening at the retina. Remember, the optics of the eye, they were there to focus that image on the retina, and particularly on the foveal retina, where we have those cones, lots of cones that are tightly packed. The photoreceptors, the rods and the cones, are the ones doing the job of transduction, and they are different from each other. So they are already shaping our experience of the visual world. They are transforming that information in specific ways. Rods and cones differ in their physical appearance, which we saw, the distribution across the retina. And again, I will encourage you to go find your blind spot, but so that we have the cones tightly packed in the fovea, no rods in the fovea. As we go out to peripheral vision, we have lots of rods and very few cones, but we do have some cones out in the periphery as well. They differ in their wiring to the brain. Because the cones have that linear circuit in the foveal vision, they get a one-to-one communication to a retinal ganglion cell, they get representation in the brain, and they give us that high acuity. They help us resolve detailed information, which is why when we're reading those little tiny letters, we need to put our foveal vision on those letters. And the convergence of information gives us sensitivity. In this case, we mean sensitivity to dim light. So the cones have some convergence of 6:1, so they're not really as sensitive to dim light. The rods have this convergence of 120 rods to one retinal ganglion cell. So a few rods are going to give us some information that there's some light out there, and if it's enough, I can get that retinal ganglion cell to fire and say, yes, I see some light out there. And we have a lot more chance of seeing it because we have a lot of those rods communicating to that retinal ganglion cell. So the wiring affects some of our clinical issues as well as some of our functional significance. Our clinical issues, I won't go back through them because I want to get back to our functional significance kind of with those. So the rods giving us our night vision. So if I have retinitis pigmentosa, I'm going to lose that convergence. I'm going to lose those rods. I'm going to lose that night vision. I can still see color, and I can still see in the foveal vision. I have that sharp vision in the fovea. The functional significance of the cones, they give us the color vision, and they give us the acuity because of the wiring, but the reason they give us the color vision is because we have those three types of cones, and we're looking at the relative firing rates of those three types of cones to give us our color vision. And so our clinical issue with the cones specifically was macular degeneration. If I'm losing those cones, then I'm going to have a more blurry spot in my foveal vision since they were all packed in there. But then I'm also going to lose my color vision as well.